Jones.
Yeah, here.
Share your screen.
Yeah. All right, can you see my screen?
Yeah.
All right, and you can hear me fine?
Welcome, Nicholas Hunter-Jones from Perimeter Institute and Stanford. Yeah, and whenever you're ready.
Yeah, sure. Okay, yeah, so I'd like to start by thanking the organizers for putting together this great workshop and for letting me speak, and of course, all of you for listening. And please feel free to interrupt with questions at any point throughout the talk if something's unclear. So today I'll be talking about some applications of ideas in quantum many-body physics and statistical mechanics to some problems in quantum information. And this is based on a few different papers, one from 2 years ago and one more recently from this past December, which was joint work with Jonas Haferkamp, who I think you'll hear from later this week. And both of these, we kind of studied a notion of pseudo-randomness and used various techniques to show that random circuits are, in some sense, random, which I'll define more precisely later. And if I have, if I have time at the end of the talk, I might also mention some additional work, which was joint with Alex Dezel and Fernando Brandao, who are at Caltech and AWS, on additional properties that random circuits satisfy. Okay. So the very broad takeaway from this talk is just that ideas from statistical mechanics and quantum many-body physics are incredibly useful for solving what I see as fundamental problems in quantum information theory. And specifically, I want to talk about random quantum circuits. And these are very interesting models for both quantum many-body physicists as well as quantum information theorists, because they're efficient implementations of randomness and are also a rare instance of a solvable model of chaotic dynamics. So in the latter sense, RQCs are valuable, in the former sense, because they're valuable resource in quantum information because they're essentially optimal decouplers. They rapidly scramble and delocalize quantum information. They're low-depth implementations of unitary designs. And as we heard about in the previous talk, the hardness of sampling from the output distribution of random circuits means that they're good candidates for demonstrating quantum advantage, such as in the recent Google supremacy experiments. If you're more of a quantum many-body physicist, you like random circuits because they're, a rare instance of a model where you can kind of directly analyze otherwise intractable quantities and study things like thermalization, the onset of chaotic dynamics, and even things like transport from diffusive hydrodynamics. Okay, so more specifically, the model I want to consider today are local random quantum circuits on a system of n qubits of local dimension q. And the evolution I want to consider is this brickwork pattern of staggered layers of two-site unitaries, where we'll act on even links at even time steps and odd links at odd time steps. And for simplicity, I'm going to draw each gate randomly in both space and time. So every gate is drawn randomly from the unitary group on two sites. And where evolution to time t is a depth t unitary, which is given as the product of t layers. Okay. And yeah, so for simplicity, I'll sort of focus on these 1D circuits, on these local circuits on a 1D chain of qubits. But we could also consider circuits defined on some arbitrary graph or in higher dimensions or even a complete graph. And we could also consider circuits where instead of drawing like these local gates randomly, we draw them from some universal gate set. And if sort of like a lot of the results I'm going to say do generalize to those cases, so feel free to ask about those cases or what might change, what kind of scalings might change if you're interested in a particular model. Right. So as I was mentioning, random circuits have appeared in a number of different archive categories. And on the more condensed matter side, they've been used to study chaotic dynamics. And there are all these interesting questions related to surface growth problems, and well, specifically the entanglement or operator growth exhibits KPZ universality in the front dynamics. And there are some nice connections to growth problems in polymers and random media. RQCs with conserved charges have been used to study diffusive hydrodynamics. And one can also consider random circuits with interspersed measurements throughout the circuit and study a volume law to area law phase transition. And as I mentioned, random circuit sampling is kind of underlies Google's claim of quantum supremacy, and I'll get back to that at the end of the talk. Okay, so a lot of these properties, these interesting properties I mentioned, can be seen as arising from one particular property possessed by random circuits, and that's their ability to rapidly generate quantum pseudo-randomness. And more specifically, what I mean is I want to study the convergence of random unitary circuits to unitary K designs. So this is the circuit depth T, where we start approximating moments of the unitary group. Okay, and just so all of my parameters, all the parameters in the talk appear on one slide, I'm going to be considering systems of n qubits, okay, where the local dimension is q. It'll turn out to be a useful parameter to play with, such that the total Hilbert space dimension is q to the n, and total Hilbert space is going to be d. Again, depth T circuits, so it's T layers, and I'm going to be interested in the kth moment of the unitary group. So those should be all the parameters in the talk. Are there any questions about the setup before I start defining things more precisely? Okay, and if questions appear in the chat, if someone could just read them out to me, I'd appreciate it. Okay, so I'll start by defining what a unitary design is, and then give sort of two proofs that random circuits form unitary designs using different ideas from many-body physics. And then we'll kind of move past designs in the last few minutes of the talk and look at another quantity called anti-concentration. Okay. So recall that the Haar measure is the unique left and right invariant measure on the unitary group. And for some ensemble of unitaries, we're often interested in moments of that ensemble. And those moments are sort of captured by an object called the k-fold channel of an operator. And that's defined for an ensemble of unitaries as this sort of average over the ensemble, right, of the kth moment. And we're often interested in when some ensemble of unitaries looks like, looks Haar random, and that'll be our notion of pseudo-randomness in this talk. And what we'll say is that an ensemble of unitaries is an exact K design if these K-fold channels are equal for all operators O, right? So the ensembles are equal up to the kth moment. Okay, so for K equals 1, Pauli's or any basis of operators forms an exact 1 design. But for general K, very little is known. Very few exact constructions are known. So to make progress, we can relax our definitions, and instead of asking when we exactly capture the kth moment of the Haar measure, we can instead ask when an ensemble looks close to Haar. More precisely, we'll say that an approximate K design is an ensemble for which the K-fold channels are close in diamond norm. Okay. And designs are a very useful notion in quantum information because they sort of allow you to wield the full power of the unitary group with relatively low complexity. And just a little bit more intuition, maybe with some pictures. What we're saying is an ensemble of unitaries. So you should picture this, this big unitary group here, and we might have some ensemble of unitaries. That's some splattering of points all over the unitary group. And what we're saying is when we average over that set of points, right, up to the kth moment, so maybe of some polynomial or monomial of KUs and KU daggers, we're saying that average over that set of points is extremely close to the average over the full unitary group, again, up to the kth moment. And maybe one more piece of intuition. We can sort of think about this as asking how random the time evolution of a system is compared to the full unitary group. Right. So in this setup, we consider an ensemble of time evolutions at a fixed time t. So these could be random quantum circuits, these things called Brownian circuits, or even some ensemble of time-independent Hamiltonian evolutions generated by an ensemble of disordered Hamiltonians. So pick your favorite spin system and disorder the couplings. Okay. At time equals 0, this is just a bunch of points sitting at the identity. But chaotic time evolution is going to move us rapidly and ergodically over the unitary group. And we can quantify how random that time evolution is by asking, at what time t do we form a K design and start approximating, capturing moments of the unitary group of the Haar measure.
There's a question, why the diamond norm?
Oh, yeah, that's a very fair question. It's sort of, I'm just going to choose that for the sake of convenience in this talk. There are definitely lots of other definitions, And even for various, so sort of the definition of a design you want to use might depend on the application you have in mind. And oftentimes that, so this is sort of some additive error. And oftentimes you might want a relative error, which requires kind of driving this epsilon down to be exponentially small. But sort of for everything I'm going to say in the talk, it's not actually going to really matter. So if you want a relative notion of design, you can just take this epsilon to be exponentially small, and that's actually going to be fine for everything I say. So it's just sort of for convenience later in the talk, given how I'm going to actually bound things. But yeah, if you have another definition of design that you like, everything I say will also hold. So you'll be able to bound your favorite definition with the diamond norm. Does that answer the question? Oh, let me know if there's a follow-up to that. Okay. Good. So actually quite a bit is known about this question of random circuits forming designs. And famously, Brandau, Harrow, and Horodetsky showed in 2012 that 1D random quantum circuits form approximate designs in a depth which scales linearly in n, and this high degree polynomial in k. Okay. And yeah, they use a beautiful set of techniques, which maybe I'll mention in a little bit, but they were also able to show they were also established a lower bound on the design depth and argued that for 1D circuits had to be linear in n and linear in k. So there was sort of some lore in the community for a number of years that random quantum circuits saturate this lower bound and form approximate designs in this optimal depth, linear in n and linear in k. Okay. And I'll get back to this in a second, but there are a few other results which I think are really nice, which I'll just briefly mention. More recently, Harrow and Mariband showed extended this result to random quantum circuits defined on a d-dimensional graph, and showed that basically higher dimensional random circuits form designs again in a sublinear scaling in n, but some high degree polynomial in k. In depth scales that way. And much more recently, these two groups from Germany showed that random Clifford circuits with kind of a polynomial number of non-Clifford gates scattered throughout the circuit form designs in a depth which scales linearly in n and some high degree polynomial in k. At least up to the first few moments. And and the number of non-Clifford gates you needed only scaled polynomial in k, but independent of n. Okay, so I should emphasize that designs are incredibly useful. They sort of pop up in every sub area of quantum information that I'm familiar with. From state distinguishability, tomography, randomized benchmarking, or the different sorts of physics applications like thermalization or fast information scrambling. And while many of these results only require maybe 2 or 4 designs, high degree designs are often essential for arguments about concentration. So saying that a single instance or a single random circuit or a single instance of your ensemble, is actually extremely close to the average. And high degree designs are also useful in understanding some long time properties of systems past equilibration. So to just give 2 examples of what I mean by that, you could consider some initial state evolved by an element, acted on by an element of a unitary K design. And you could ask how close the subsystem, the entropy of some subsystem is to its thermal value, to its equilibrium value. And what you can prove is that the probability that that subsystem entropy deviates from its equilibrium value is exponentially suppressed in the total Hilbert space dimension by powers of K. Okay, so if you know that you have some time evolving system, and you know that that time evolving system is forming designs as it evolves, then what you can show is that the fluctuations of subsystem entropies, continue to get rarer and rarer in time and keep getting suppressed by additional powers of the total Hilbert space dimension, all the way up to potentially exponential times. So sort of what this is saying is, and one thing you can use designs to prove is that maybe subsystems of many body systems are a lot more static than you might have thought. And another use of designs in understanding the post-equilibration properties of many body systems is in understanding the growth of quantum complexity. So by here I'm referring to the circuit complexity. which is the minimal circuit required to approximately prepare or implement your unitary. And you can show that the complexity of an element from a design scales linearly in K. So if you're then able to prove that your time evolution generates designs as it grows in time, as you time evolve, then you can prove that some lower bound on the complexity growth. Okay, so this Brandau-Harrow-Hordetsky result I mentioned gives a lower bound, which is the slow growth in time. But if you're able to prove a linear growth in design, you would then establish a conjectured linear growth of complexity, where it's been conjectured that most local random quantum circuits of depth t have a complexity which scales linearly in time for an exponentially long time. Okay, so these are just sort of two examples of where high degree designs are interesting from like a physics point of view of understanding many body systems. Okay, so to get back to designs, we want to study the circuit depth at which random quantum circuits start forming designs, and I'm just going to sort of briefly present two theorems using different ideas from quantum many-body physics and statistical mechanics, which establish this optimal behavior, or almost optimal behavior. So this linear scaling in n and k, if you allow yourself to play with the local dimension. Okay. And the two approaches I'm going to use to compute the design depth for random quantum circuits involve upper bounding the partition function of a lattice model and lower bounding the spectral gap of a local Hamiltonian. So before I get into the main content of the talk, I'll just pause for questions. So are there any questions about anything I've said, or what the setup is, or why I'm interested in what I'm doing? If there are more questions, again, feel free to write them into the chat. So I'll just focus on the first approach. And recall I defined a unitary design in terms of this diamond norm, but diamond norms are famously hard to compute. So we're going to take a retreat to a more tractable notion of Haar randomness. And to do this, I'm going to consider the kth moment operators for the ensemble of unitaries, which is given by this object here. And this allows us to define a more tractable notion of Haar randomness, because we can consider the two-norm distance between the moment operator, the kth moment operator of the ensemble we're interested in, and the Haar ensemble. And this two-norm can be conveniently written in terms of something called the kth frame potential for the ensemble. Okay, so this frame potential is just defined as this sort of double average over all the inner products of your design elements. And for an ensemble of unitaries, the kth frame potential is lower bounded by k factorial with equality if and only if you form an exact k design. Okay, so what this is saying is if you hand me some ensemble of unitaries, you can compute this frame potential for a given k, and how close, and you'll get some number, and how close that number is to k factorial tells you how close you are to forming a design in two-norm distance. Okay. And then, I defined designs in terms of this diamond norm. So we'll need to we'll be able to upper bound the diamond norm using this weaker norm, just by showing basically that this difference is exponentially small. Okay. So the goal now is to compute this frame potential for random quantum circuits evolved to time t. Right. So the ensemble we're interested in is depth t random quantum circuits. And to compute this quantity, basically this is just moments of traces of random quantum circuits. It's some kth moment quantity, so we need to do some kth moment average of random quantum circuits, for which we need to consider k copies of the circuit and its conjugate. And in performing this average, we're just basically averaging over all these two-site unitaries. And if you recall, you can kind of understand averaging these gates, doing these local averages as basically Haar averaging is sort of a prescription for index contraction. So there's a way to rewrite these averages over the two-site unitaries in terms of a way to keep track of all these index contractions, and you can write these local averages as some effective plaquette term. And what that allows you to do is define this frame potential or rewrite this frame potential as the partition function on a triangular lattice model. Okay, so I'm skipping over a lot of details, but basically, when you do this average, there's some massive index contractions, which that Haar average tells you need to sum over, and with given weights. And basically, those contractions are you're contracting these indices with respect to some element of the symmetric group Sk, and we're just keeping track of all those with basically some nice tensor network diagrams where the local degrees of some nice lattice model where the local degrees of freedom are elements of the symmetric group, and these lines encode the weight of a given contraction, roughly speaking. But the end result is that this frame potential can be exactly written as the partition function on a lattice model, where this lattice model has width n over 2, depth 2t, and with periodic boundary conditions in time. So all these nodes here are identified with all these nodes up here. And the local degrees of freedom are, again, elements of Sk. And the weight of a given spin configuration is given by the product of plaquette terms. And a given plaquette term is a function of 3 spins, which is just can be exactly written as this function here. But it's not too important what this is. It's just some function we can compute. And then, it's a partition function in the sense that we sum over all overall spin configurations, with weights determined as I just said. All right. So the first thing you can show is that by plugging in the same spin everywhere, on this lattice, you have a weight 1. And thus we can already see where this minimal Haar value comes from. So I told you that this frame potential is lower bounded by a k factorial. And this value comes from the k factorial ground states of the lattice model, right? So there are k factorial ways we can plug in the same spin everywhere. So the decay to Haar randomness must come from the decreasing contribution of all the excited states, higher order terms in this partition function. Right? And kind of trivially, if you plug in, for the first moment, there's only one way to plug in the same spin everywhere. So there's just one configuration for the first frame potential. So the frame potential is just 1, and random quantum circuits form exact 1 designs. But the second moment is non-trivial. And there, all non-zero contributions to this partition function are domain walls. Could be thought about as domain walls in the lattice model, which must wrap the circuit. So for the second moment, here's an example of a single domain wall configuration or a double domain wall configuration. So this is for the second moment where the local degrees of freedom are elements of the symmetric group S2. So we have some region of identities and some region of swaps, and we can think about that spin configuration in terms of the domain wall separating the regions of identities and swaps. So to compute the second frame potential, to understand how the convergence to approximate 2 designs, we just simply need to count all the possible domain wall configurations. Sort of for general K, you always have K factorial ground states. Then you can sort of think about the single domain wall configurations, the double domain wall configurations, and it's just some messy combinatorial procedure to sort of compute or bound those possible contributions. But we see that the decay to Haar randomness comes from the sort of stretching of the domain walls as we evolve the circuit, right? So as we evolve in time, these circuits get deeper and deeper. These domain walls, you can think about them as basically stretching, thus contributing higher energy and lower partition weight to the sum. Okay. So for the second frame potential, kind of upper bounding all these terms is pretty straightforward. And what you find is this. And that allows you to directly compute the circuit depth where you form an approximate 2 design. It's basically just n plus log 1 over epsilon. Or more precisely, it's this sort of the bound on the 2 design depth is this with some exact determination of the coefficients. Okay. And it's maybe fun just to mention that you can actually compute the k equals 2 partition function exactly without having to kind of upper bound the domain wall configurations by solving the problem of p non-intersecting random walkers on a line. And that makes use of some nice statistical physics ideas from the 80s. But for our purposes, all we need is the upper bound. And for general K, this same picture holds, but we sort of the picture for K equals 2 is a lot simpler because you just have one type of domain wall, and it's pretty straightforward to bound all the domain wall configurations and compute this partition function. But for general K, there are a lot more types of domain walls, it turns out, and they're allowed to interact, pair, create, and annihilate. And this basically means the combinatorics of domain wall counting are a lot less amenable to a precise treatment. But there are two things you can prove, or a few things you can prove, which allow you to say something useful. So for general K, as I said, you always know that you have this contribution from the ground states. Basically, you always know that there are K factorial ground states of weight 1. And you can also exactly compute the contribution from the single domain wall terms. And you just find this expression here. And it's sort of the higher order terms that are a mess to bound. But what you can further prove is that all higher order terms, which are multi-domain wall terms, are heavily suppressed and necessarily must be subleading in 1 over Q. So they're suppressed, additionally suppressed by powers of the local dimension Q. And what that allows you to show is that for some local dimension, which, for some large value of the local dimension, this sector of single domain wall terms needs to dominate. And you just do the calculation and you find from the single domain wall sector, the design depth is this optimal value, which is linear in N and K. So just to reiterate, what we've shown using this two-norm approach is that random quantum circuits on n qubits form approximate K designs when the depth is at least linear in N and K for some large value of the local dimension. And again, this is a rigorous statement in large Q, but there are a number of reasons why I think this limit of large local dimension is not necessary. So I just sort of left it as a conjecture that for any local dimension Q, the single domain wall sector of this lattice partition function needs to bound the basically higher order terms. So the higher order terms are basically conjecturing they're small for even Q equals 2. But as the lower bound on the design depth is linear in N and K, what we've then shown is that random quantum circuits are then optimal implementations of this notion of pseudo-randomness, at least in this limit of large local dimension. So that was the first approach to showing that random quantum circuits form designs. Are there any questions about this method or this approach? Pause for a few seconds. Okay, so the second approach I want to talk about involves lower bounding the spectral gap. And this involves a retreat to a different notion of design. So instead, we're going to focus on the operator norm difference of these moment operators. And for depth T random quantum circuits, this operator norm has two very nice properties. So the first is amplification. So what this says is that we have to look at this operator norm difference of the moment operators for the ensemble of random quantum circuits and the Haar ensemble. But you don't actually need to consider this basically full depth T random quantum circuits. Just sort of every time you act with another layer, this operator norm just gets amplified by some power T. Okay, so you don't actually need to consider the full depth T random quantum circuits. We just sort of need to consider this action of a single layer, or the moment operator for a single layer. And then the second nice property is that this operator norm for the moment operator of a single layer can be reinterpreted as the gap of a local Hamiltonian. So we can bound this difference by the gap of some local Hamiltonian, where you should sort of think about these local terms as the local moment operators for the gates themselves. So you should sort of think about the terms of the Hamiltonian as like as like a sum over the sort of the projection operators, which are themselves the gates in the random quantum circuit. So as you can see here, if you compute this spectral gap and you show that it's 0, right, then this operator norm is just less than 1, and if we amplify 1, we don't learn anything. So we need some sort of non-trivial lower bound on the spectral gap of this Hamiltonian to to have some useful amplification as we evolve in time, which will then give us some convergence to a K design. Okay, so we need some non-trivial lower bound on this on the spectral gap of this Hamiltonian. So there are a few nice properties that this Hamiltonian possesses. It's the sum of projectors. The Hamiltonian is a sum of projectors. It has ground state energy 0, and it is frustration-free. So I think Norbert mentioned frustration-free Hamiltonians briefly in his talk 2 talks ago. But just to reiterate, a frustration-free Hamiltonian is one where the ground state of the Hamiltonian is also the ground state of each term in the Hamiltonian. So in that sense, it's not frustrated because these local terms aren't fighting to reduce the energy. Said equivalently, there is an element in the intersection of the kernels of all these projectors. And I said we need to lower bound the spectral gap of this Hamiltonian. And actually quite a lot is known about lower bounds on spectral gaps of frustration-free Hamiltonians. So notably, there's this beautiful theorem by Knabe, which says that for 1D translationally invariant frustration-free Hamiltonians, the spectral gap for the Hamiltonian on n sites is lower bounded by this quantity here, which involves the spectral gap of the Hamiltonian on 3 sites. Right? So this is called a finite size criteria because you just sort of need to check the gap of the Hamiltonian on some small subsystem, and then that allows you to say something about the spectral gap of the Hamiltonian for all n. So what you have to do is you have to go in and check spectral gap on 3 sites, and if it's larger than 1/2, then you're done. Sort of show that it's gapped for all n. Right, so just to kind of recap the steps we've taken for this operator norm approach, amplification has told, we're considering depth T random quantum circuits, and amplification tells us we don't actually need to consider, full depth T random quantum circuits. We just sort of need to think about a single layer of the circuit, which by which I actually meant sort of an even layer and an odd layer. And then we reinterpreted this as a spectral gap, basically using the detectability lemma to break down of these gates into a sum over the gates, very roughly speaking, and then basically reinterpreted that operator norm as the lower bound on the spectral gap of a Hamiltonian defined this way. And then Knabe bounds told us that we actually don't need to consider the Hamiltonian on n qubits on n sites. You just need to consider the Hamiltonian on 3 sites. Okay. So what you can then go ahead and show is that, well, first you can exactly compute the second moment gap for k, again, k equals 2 and n equals 3, and you can see that it's 3/5. And you go up here to the Knabe bound, you look at 3/5, and indeed it's larger than 1/2, so you're done. Through this series of steps, you've shown that random quantum circuits form approximate 2 designs. Moreover, you can use sort of the almost orthogonality of the ground states of this Hamiltonian to show that if you take the local dimension q to be larger than 6 times k squared, then the spectral gap on 3 sites for any k, okay, is lower bounded by 3/4, and 3/4 is larger than 1/2, so we're done. And what those two things allow you to conclude, these lower bounds on the n equals 3 gap allow you to conclude, is that random quantum circuits form approximate 2 designs in this depth. And when the local dimension is at least this value, you form approximate designs in this almost optimal depth. So before we had this behavior that was linear in n and k, and now here we actually just have an additional log q factor. So it's a much better scaling. Before we just had this kind of unbounded, this kind of this requirement that the local dimension needed to be large in some way we couldn't really control. But here we have a much more controlled local dimension, but we have this additional log q factor, which is pretty minor in the design depth. Okay, so this is nice. We've sort of shown that for maybe possibly reasonable local dimensions, you get this optimal behavior for random quantum circuits. And I'll just briefly mention 2 other things. For near-term applications of random quantum circuits, this spectral gap approach is actually nice because if you're just interested in maybe the first few moments, the constants involved are actually important, and you can just go ahead and analytically or numerically compute these spectral gaps, and they allow you to write down good constants for the first few moments for random circuits you might be interested in. So that's nice for maybe near-term applications where you just need the first few moments. You don't need these very high moments, but you do need good constants. You can also use the spectral gap approach to improve the design depth for non-local random circuits. So everything I mentioned so far was for 1D circuits, but obviously these techniques work for circuits defined on other graphs. And yeah, by showing some sort of recursion relation on the spectral gaps, you can actually improve the N and the K scaling for non-local random quantum circuits using the spectral gap approach. Okay, so are there any questions about spectral gaps or these either proof random quantum circuits form designs?
There was a comment in the Q&A saying it was confusing that T is both thickness and time, but I guess there's a reason for that.
Sorry, T is both what?
Thickness and time, but I guess that's.
Oh, I mean, I just. I hope that wasn't confusing. That was, I mean, so T throughout this talk is only the circuit depth, and I'm calling that time. So
right. Yeah, just to.
Yeah. So just to reiterate for anyone listening, what I mean by time is the circuit depth. So that's sort of a definition. Yeah. And yeah, I mean, it sort of, maybe it depends on how you orientate your circuits, but I think about the thickness of the circuits as like N, and then the depth as sort of as T, but it doesn't really matter. Okay, so just in the last few minutes, I'll just mention how some of these techniques can be useful for understanding properties which go beyond this notion of pseudo-randomness, go beyond designs. And this is more relevant for different notions of quantum supremacy. So as you all know, recently Google did an experiment where they claimed to have done some task which was intractable for a classical computer. And they actually ran some random circuit on 53 qubits with a circuit depth around 20, where their qubits were on were arranged on a 2D geometry. And so they ran this random circuit, they measured in the computational basis, and the classical distribution you get over the output probabilities, they claimed that sampling from that output distribution is not possible on a classical computer. Okay, and I won't go into too many details because Bill gave a beautiful overview of this subject in the previous talk. But very roughly speaking, we know that exactly computing these output probabilities is worst case hard. And what you need to show to establish this conjecture is that, very roughly speaking, some approximate average case hardness for these output probabilities. So they're at a given precision. So one ingredient in arguments in the hardness arguments for random circuit sampling is something called anti-concentration. And anti-concentration basically says that these output probabilities, this distribution over measurement outcomes, are sufficiently spread out. Okay. And the fact that they're spread out is sort of some additional robustness guarantee that says that the signal is large relative to the noise. And more precisely, what I mean by anti-concentration is they'll say that an ensemble of random quantum circuits is anti-concentrated if the square of these output probabilities is basically within some constant of the Haar value, which is 1 over d squared, or 1 over q to the 2n. Okay. So what we're able to do is we kind of applied these StatMech techniques to compute the depth at which random quantum circuits anti-concentrate. And with Alex Wiesel and Fernando Brandao, what we showed is that for both 1D circuits and random circuits defined on a complete graph, for n qubits, these random circuits anti-concentrate when the circuits are of size n log n, which roughly corresponds to log n depth. Okay, so this is exponentially faster than the 2 design depth, which is a sufficient but not necessary condition for anti-concentration. Good. So that was all I wanted to mention. It was just sort of an overview of the different ideas in many-body physics and statistical mechanics, which allow you to compute quantities of interest for random circuits. And I mentioned these sort of results for showing that random circuits form unitary designs, and also you can apply similar techniques to study anti-concentration. And there are a lot of open questions that I still have about showing that this linear design growth holds for any local dimension Q. and for exponentially long times. It would also be nice to prove that the design depth for non-local random circuits, so defined on a complete graph, is n log n times, is log n times k. And I think these step-mech approaches are very powerful, and people have generalized them in all sorts of different ways, but I think there's a lot of room to study, kind of other generalizations of random quantum circuits themselves, like adding conservation laws or sort of adding some periodicity in time. But maybe that's all I'll mention for now. So thanks for listening, and let me know if you have any questions.
So I guess one question, maybe a basic question. So is it clear that like the gate sets that you're using for like?
Sorry, I can't hear you very clearly.
I think I can barely hear, but maybe if you speak up a little bit.
Okay. I'll try.
No,
is it clear that so like how does the gate set that you're sampling over for the random quantum circuits affect any of the parameters, or is it somehow clear that it doesn't affect the parameters?
Yeah, that's an excellent question. And I sort of intentionally glossed over this, but it's right. So at the beginning, I said that my results will hold for more general gate sets, but sort of in all the actual calculations I did, I used random local gates. So I just averaged over generic local gates. So for this first approach where I use the 2 norm, there isn't a direct generalization to universal gate sets, but in the second approach there is. So I don't know what a good slide to pause on is. Just go here. Yeah, so when you're looking at this this operator norm, yeah, again, you're computing this quantity for random local gates, but it is known that the spectral gap for universal gate sets, basically the operator norm for the moment operator between random local gates and any universal gate set is just some constant. So what that allows you to show is that basically the spectral gap results need to hold with the same scaling in n and k, and you'll only change the design depth by a constant. So in the second approach, it's known that you can generalize to universal gate sets. There's some additional restrictions, like you need to, the gate set needs to involve inverses and only can have algebraic entries in the gates. But apart from those minor caveats, all these spectral gap approaches hold with the same scaling in n and k. You just change the answer by a constant, and that constant will depend on the gate set. So obviously you can choose gate sets where the constants will be, really bad and potentially, extremely large. And random should probably be the correspond to a nearly optimal constant. Does that answer the question?
Yeah. Yeah. A second question. So how do these notions of K designs and like anti-concentration compare to like generating a pseudo-random state?
Yeah, so I was maybe a little liberal with, I mean, this is sort of how I think about pseudo-randomness, but it's a very strong notion of pseudo-randomness in that, so it is sort of like a quantum analog of KY's independent distributions, but these sets of random circuits are like sort of K designs themselves are maybe overkill in that they involve, sort of the cardinality of these sets is necessarily exponentially large. So there are lower bounds on the number of elements you need in a design, and they're necessarily large. So I think for K designs are sufficient for a lot of cryptographic notions of pseudo-randomness, but probably they're overkill. But they also satisfy. You can also show that designs are very strong in that they satisfy additional strong properties, like you can't distinguish some state acted on by a design basically in any way that's more efficient than just undoing that circuit. So if it's okay, yeah, I just sort of defined this as my notion of pseudo-randomness. It's just a strong notion of pseudo-randomness. Does that sort of answer the question?
Okay, so looks like there are no more questions. Are there any closing remarks from any of the organizers? Otherwise, I guess we are coming to the meeting is coming to an end for today. So we'll see each other tomorrow.